This week, I've been considering what an electrician actually does. And I don't mean that to sound offensive. Of course, the obvious, they design, install and maintain electrical systems. But everything that an electrician does is either guided or based in principle on providing protection. Protection to people, protection to animals and protection to buildings. The regulations that electricians need to follow to keep things safe has changed over the years. We'll get into that a little bit more next week. You'll see. Let's look a little bit deeper into some of the protections that an electrician puts in place, breaking down this week's learning. One of the biggest problems for humans with electricity is that electricity can conduct through our bodies, and generally that isn't a good thing, surprise. It can cause problems such as burns and effects on the heart, to name two. Although, if you're having a heart attack, it could be a good thing. Over the years, many different methods to protect people from the effects of electricity have been developed. The first step is to provide insulation on the cables. Believe it or not, conductors haven't always been insulated as they are now, with minimum cotton insulation to keep the electricity in back in the early days of electricity, when it was only really used for lighting. And yes, there's many situations today where conductors are not insulated, such as power lines that people can't reach, or bus bars which could be inside an enclosure. But a couple of hundred years ago, we're talking about cables going through properties with very little insulation. That brings me nicely onto barriers and enclosures or obstacles to prevent access. Think of all the touchy bits of a consumer unit that are buried inside that consumer unit, behind screws. The same goes for sockets, corded appliances and so on. This is where our international protection codes come in. Our big book gives requirements for different levels of protection for different situations. To put meat on the bones, as it were, to our IP ratings, the regs say in 416.2.1 that enclosures are required to meet IP2X, but later on in 416.2.2 the horizontal top surface is to meet IP4X, meaning in simple terms that you wouldn't be able to get a finger in the consumer unit or a cable in the top without tool to remove the cover. Simple, right? And it's all there for safety. You might think that electricians just install consumer units that are already up to regs, so it doesn't matter to them. Well, that's partially true. They do have to use consumer units that are up to regs, but they'll also potentially be drilling holes to allow cables to go into that consumer unit, so they need to make sure that when they're finished, they meet the standard. Another method of protection is an isolation transformer, which we find in bathrooms for shavers and toothbrushes. This means that there is no electrical path for current to flow through you unless you touch both the line and neutral to be completing a circuit, but that's very rare because of those barriers not allowing you to get to those wires. In most cases, we want an earth path to detect and interrupt fault currents to protect the circuit from overloading or short circuit. Ow! This is what we call fault protection. Fault protection is covered in Part 4 of BS 7671. How is this achieved? We start off by having our protective potential bonding to our gas and water pipes and automatic disconnection of supply, such as breakers or fuses. We also have Class 2 equipment, which are fully isolated with double insulation. We might have electrical separation, like we talked about before with our isolation transformer, or we could have SELV, a low enough voltage that would not harm human life. And these are just a few methods of fault protection. Part of the job of protecting people is protecting the cables, and this is done with our protective devices such as our circuit breaker. When a fault occurs either by current passing to earth or overloading a higher than designed current, in these scenarios it will cause the breaker to trip because it would have the appropriate cable and the breaker which would follow the regs, right? When we think of overloading, we might think of a chain of extensions which rely on a fuse to break the connection. But overloading could mean an entire circuit, say a ring main. We could easily plug too many high-powered devices, which would cause the cable to pull too many amps for its design current. Interestingly, it's not just sockets that could cause this overloading. Even a stalled motor can draw more current. A stalled motor draws way more current than its general operating current, which could cause this tripping effect. All of what we've discussed so far is what I've been learning this week, and I definitely haven't found this out from my own experience. Sometimes the causes of faults are obvious. Say for example, you know you've plugged too many devices in, or you know you've caused a fault by putting a nail or a screw through a cable in a wall. But sometimes faults are far less obvious, which is why you should call an electrician if it's not an obvious fault, because there is a reason why things trip. So, from a regulation point of view, we can understand why all these breakers need to meet a certain standard, why all the fuses need to meet a certain standard, why all the cables need to meet a certain standard. This means that we know exactly what we're dealing with and how they'll react in each of these circumstances. Using all these standards recorded within the regs book, we're able to design circuits with a consistent outcome. How much of a mess would things be in if we didn't have all these pieces of information to design circuits? Well, you only have to look in the past, hey? We can also protect cables by making sure that they're supported, following regulation 522.8.4 of BS 7671. The regs also consider cable bends. Radiuses that are too tight can cause insulation to be stretched beyond its design. It could also cause the conductor to develop a higher resistance at that point, effectively making that bit of cable thinner, which could cause a hotspot. And as we know, hotspots mean that the cable is not going to work as it's designed to, and that there's a risk of fire. Talking of fire, we get into protecting fires from spreading through the holes which electrical cables pass through. The old school way was to leave these holes as they were and just poke the cable through, but regulations such as 527.2.1 require a degree of fire resistance, and there's quite a few different methods for ensuring this. Basically, we want to reinstate the hole that we've put in. Another way to protect cables to ensure that they're within cable zones. This means that they would be horizontal or vertical from accessories, or to use the corners or edges of walls. This gives us quite a number of areas that we can run cables. Given that most nails or screws for wall fixings are generally going to be under 50mm in length, think of the average raw plug, there is also requirements to place cables at a depth of more than 50mm, and according to the regulation 522.6, if it's below 50mm, then they'd need to be protected to prevent penetration. So that would protect the cable. And then for protecting people, in this situation we got regulation 522.6.201, which touches on an RCD being needed if it's not possible to put the cable deeper than 50mm. The same 50mm depth is not just for walls. Joists are covered too. We want our joists to be drilled with a depth of 50mm on either side of that joist. That means that any plasterboard or flooring that's put down isn't going to have a screw that goes through our cable. Again, if it's going to be less than 50mm, say that there's a notch cut out in the top of a joist, we'd look to regulation 522.6. 522.2.1 touches on protecting cable against heat damage. Remember, heat damage is going to cause a higher resistance, which will cause heat, which will ultimately cause the cable to be damaged to the point of fire. A lot of the regs cover the conditions that the wiring is going to face. Things such as temperature, moisture, or sunlight. These are just a few. Some of these effects we looked at a couple of weeks ago when we talked about how we would design a circuit and choose the correct cable and protective device. Remember, we talked about how the cable would run through insulation and how that would affect the rating of the cable, effectively downrating that cable. So we needed to make sure that we had a cable that would stay within the correct temperatures. I'll pop a link to that up here if you haven't already seen that. One more consideration that I looked at in the regs this week was that the human resistivity of our bodies drops when our skin is wet. This creates a path for current to be able to flow much easier than if it was dry. So, the areas where we might likely to be wet, such as bathrooms, are identified as a particular risk. In bathrooms, we have wet conditions along with wet humans. This is where we get our zones in bathrooms, areas that we need to provide extra protection to avoid human contact with electricity. We might use extra low voltage or IP rated devices. For example, we might use LED lighting in a bath or an electric shower with an IP rating. This is all covered in Regulation 701. This allows me to finish this week on one of my favourite electrical items, which I think we should have absolutely everywhere, and all old systems should be upgraded to this, in my view, RCD. These bathroom locations, according to Regulation 701.411.3.3, require RCDs to provide extra protection to the people in these environments. But come on, we should have them everywhere, shouldn't we? Let me know what you think in the comments below. Until next time, Battery Man out. This means that the horizontal, that's not horizontal,